Hello everyone. Today we're going to continue the lesson from the other day on quadratic transformations. And today we're going to be looking at vertical compressions and stretches. So just to remind you of what equation we're looking at. So we're looking at the equation for transformations of parabolas, which is y is equal to a times x minus h squared plus k. And what we've seen so far is the x squared plus k version of the equation. And we saw that the k value, if it's positive, will cause a vertical translation, which means sliding up or down. In the case of a positive k, it'll slide it up. In the case of a negative k, it'll slide it down. So we're already starting to control our parabola. Now, why would we want to do that? Well, there's an example in your textbook. I'll just read through it. It says, predict the equation of a parabola without using technology. So during the filming of the Lord of the Rings trilogy, Andy Serkis, the actor who played the character Gollum, wore a motion capture suit. The motion of the dots on the suit was analyzed by computer to model the motion of the computer-generated image of Gollum. Suppose it makes sense to have negative time values. The graph shows Gollum's height above the ground over time as he jumped from one rock to another. Write an equation, or write a relation, in the form of y is equal to ax squared plus k to represent Gollum's jump. So this is a real-world scenario here, a mathematical one, where somebody has to program a computer to be able to follow the dots on a suit. And we know that when things fall in gravity, that they actually do follow a parabolic path. Or a parabolic pattern, because even if they're falling straight up and down, the distance to the ground increases as they're falling every second following a parabolic pattern. So I'm not going to get into that too much. That's a little bit of physics there. I might talk about that a little later on. But basically, can you find an equation to match this graph is a thing that scientists and mathematicians do all the time. That's all that math is here's a pattern. Can you find an equation to match that pattern? And the reason we want an equation is to be able to predict future values and past values that could potentially lie along that curve, and to use it to analyze other curves that might be similar to it. Okay. So it's like most scientists and mathematicians, when they study in university, this is almost all they do, is look at patterns and try to find equations for them. Right? So we're going to give you a little glimpse of that today. So you'll notice that this equation here, and I'll write it off to the side, has another letter added to it from yesterday's equation. And that letter is A. So what does the A do? When you multiply times x squared a certain number, how does that change the parabola? So what we're going to do is we're going to start with just looking at how A affects the equation. So we're going to do A times x squared. We're going to forget about the k, and we're going to try to see how does A affect the equation. Now, just to give you a few hints as to where we're heading, you can clearly see that this parabola right here doesn't look like the parabola that we were working with in the other lesson. The parabola we were working with, and it's very hard to draw on my tablet to make it look pretty, folks, but the parabola we were working with was a parabola that basically looked like this, right? Well, the dots don't follow that pattern. So how can we change this parabola so that it does follow those dots? And that's what we're going to be, that's our puzzle for today. That's what we're going to try to solve. Now, we actually do know one thing. This is the vertex. The vertex is now somewhere up here. That is a vertical translation. So we at least know that the vertex has slid up by 6 approximately. So most likely our k value is going to be 6 or somewhere around 6. Okay, so we at least know that much from yesterday's lesson. So this is a vertical translation. And we know how to slide things up or down now. We just change the value of k. Because it's moving up, it's going to be positive, and it certainly looks like it's going to be somewhere around 6. all right? But how do we get it to be upside down? And it seems to be wider than our parabola was yesterday as well. So we're going to analyze that, and to help us analyze that, we're going to go back to one of my favorite tools, which is Desmos. I can find it here. There we go. Okay, so all I did was I basically reproduced that graph, and I didn't use the exact same points that they had because I wasn't sure exactly what the points were, but I was able to estimate a few of them, and I used the idea of symmetry to kind of make it a nice parabola, okay? And we'll come back to this later, all right? So I'm just going to turn this graph off for now so it's not in our way, but this is the puzzle that we're trying to solve, okay? We're trying to find the equation for this graph. All right. Now it says to do it without technology, but I'm going to use technology to help us understand what's going on, and then I'll show you how you would do it without technology. Okay. So let's start with our y is equal to x squared equation, which is our regular parabola. We know that that regular parabola has a table of values, so I'm going to add a table of values here. And I'm going to go from -2 to positive 2 today. Yesterday I was going from -3, but as I explained at the end of that lesson, sorry, I say yesterday, but I mean the last lesson, that we don't necessarily have to go from -3 to 3. If we go from -2 to 2, it should be fine. And if you remember how we generate our regular y values for our regular parabola, y equals x squared tells us how to do that. So you take the x value and you square it. So -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. Okay? So that's our table of values. You can see the points that are following the parabola, right? What would happen if I wrote y is equal to 3x squared? So I'm going to generate another table of values, and we're going to compare it to the first one. So we're going to go -2, -1, 0, 1, 2. Okay. Now I don't want to write the equation, because if I write the equation, Desmos will just graph it and you'll see the answer. Okay. But I want to talk about the table of values, because if you can understand how the table of values changes, it's going to help you understand how the graph changes as well. So remember, the y values are just the heights of the points, right? So at a -2, we have a height of 4 right there. At -1, we have a height of 1, 0 a height of 0, 1 a height of 1, 2 a height of 4. So those are the heights of those points. If I wrote y is equal to 3x squared, how would the y values in the table change? Well, what does 3x squared mean? It means 3 times the x squared values that we had. Well, our x squared values are the heights of our points. So the height of my point here is 4, right? Right there is 4. I want to do a height that's 3 times bigger than that. So what is 3 times 4? Well, 3 times 4 is 12. Now, 12 is way up here. Now notice that it's not on the red line. It has been transformed, because this height has become this height. So it looks like we've stretched things out, right? So what would be the next height? Well, my next height is 1 regularly. I want to do times 3. Well, what's 1 times 3? It's 3. What's the next height is 0 times 3, which is 0. Now that one's interesting. That one doesn't change. The purple dot, and I'll show you the purple dot for 0 is right here. The green dot for 0 is at the same spot. And that's because, and when you multiply by 0, the answer is still 0. Now we can use symmetry to finish this off, or we can use the idea of multiplying by 3. So 1 times 3 is 3, but symmetrically, right? If this height was 3 right here, then the next height is also going to be 3. And then the next one's going to be 12. look at the green dots, and I'm about to draw the equation through there. Okay, look at the green dots. We call this a stretch because we took this height and stretched it to this one. We took this height, and we stretched it to this one. So that is a vertical stretch of the points. So let's look at what the equation of this graph would look like. Y is equal to 3 times x to the power of 2. And the black graph is showing us that stretched parabola. Okay? So I've seen this described as if you were to draw a parabola on a balloon that was half inflated, and then stretch that balloon, or not a balloon, like a piece of rubber from a balloon kind of thing. So if you drew a parabola on a piece of rubber and then stretch that piece of rubber upwards, what would the new parabola look like? Well, it would be stretched to look like this one. Okay? Now, what's special about the number 3? Well, what other kind of numbers would stretch the parabola? Well, any number that's greater than 1, right? So 4, you'd be multiplying all your y values by 4. So let's just show that. So what happens if it was y equals 4x squared? Now it's getting a little bit messy here, so I'm just going to get rid of the red original parabola. But the black one was the 3x squared. The new red one is the 4x squared. Well, look at the 4x squared is even more stretched because it's 4 times the original dots. Okay, so this point here, which is the table of values, the height is 1. Multiply 1 by 4, you get a new point here at 4. Okay, well, let's make this even more dramatic. What if I did 10 times x squared? Look at how much stretched out that red parabola is now. What if I did 100 times x squared? Look at how stretched out that parabola is now. Okay, so we can now control how stretched out the parabola is vertically, and when you stretch a parabola vertically, you're making it narrower and narrower. Okay, so as the numbers get bigger and bigger, the parabola gets narrower and narrower. Now, the puzzle that we're trying to solve, I'm going to turn off this table now because we don't need it anymore, and I'm going to bring up this table again. The puzzle we're trying to solve has an upside down parabola. Now, what kind of multiplication would cause an upside down parabola? What kind of number would I have to multiply in front of x squared to cause an upside down parabola? So take your original table of values here, okay, this one here, and we want to make the y values upside down. Well, I'm going to turn that parabola back on, turn this one off. Okay, so I'll turn the y equals x squared parabola back on, and I'll turn these two off. Actually, I'm just going to delete these two. We don't need them anymore. Okay, so this is our original parabola, y is equal x squared. I want these points to be upside down. Well, where would upside down bring them? 1 has a height of 1 right here. Wouldn't that become a height of -1 if it went upside down? Wouldn't this height of 4 flip over and become -4 if it was upside down? So what kind of number is going to turn a parabola upside down? So what I'm going to do to show you that is I'm going to plot all of the regular y values from our original parabola with a negative number in front of them. So -4, -1. Now 0 negative is still 0. Again, -1 and -4. And if we turn that parabola on, it is a perfect parabola, but is now upside down. So positive numbers will stretch the parabola if they're greater than 1. Negative numbers will flip the parabola upside down. Now, do they also stretch the parabola? Now, this is just -1, right? So I'm going to show you that with an equation. And I'm going to get rid of that. I don't think I need those tables of values anymore. I think we're going to concentrate more on the equation now. So if I do y is equal to negative x to the power of 2, sorry, -1, wow, x to the power of 2, there is that -1x to the power of 2. And you'll notice that it's exactly the same shape as the red parabola, or the parabola on top, just flipped upside down on the bottom. But what if I change the -1 to a -2? Is that the same shape? The bottom parabola now looks narrower than the top parabola. What if I change the equation to -10? Whoa, that's a much more dramatic, narrower parabola. So we've got to be careful when we say stretches when they're upside down. We have to state that a negative number does two things to the parabola. It flips it upside down, and it causes a stretch as well if the number is greater than 1. Okay? So keep that in mind. Now, what do we call a flipped upside down mathematically? A flipped upside down mathematically is called a reflection. So let's take a minute and go back to our smartboard here. And let's write some of this information down. Okay, so I'm just going to switch pages here. So, summary so far of y is equal to ax squared. So we're looking at the a value, and what does the a value do? So if, sorry about that, if a is a number greater than 1, the parabola will be stretched. If a is a negative number, the parabola will be upside down. And when we flip something upside down, that is called a vertical reflection. Vertical reflection. Okay? Now we have to be careful when we say if a is a number greater than 1. Just a quick little talking about, I'm just going to talk about this quickly because it's a little bit confusing. If I write y is equal to -3x squared, okay, is -3 greater than 1? If we think of our number line, 1 is here, -3 is here. We consider -3 to actually be smaller than 1. It's a smaller number than 1, all right? But the problem is there's two different things happening. There's the negative sign effect and the 3's number effect, okay? So you kind of, when you're talking about transformations, you got to kind of keep those two things a little bit separate. You've got to think of the 3 as being greater than 1, and the negative sign as meaning flipping it upside down or reflection. So greater than 1 is, I don't know if I should put this in quotes, okay? It means the a value without the sign, what is its function, and then the negative sign separately, what is its function, okay? And I'm not going to explain it more than that because I feel like it should be understandable that if the value of a without the negative sign is greater than 1, that you're going to have a stretch, and if it's negative, it's then also going to reflect. Okay? So we've summarized those two pieces of information. we're almost to the point where we might be able to figure out what that graph is. Let's go back to Desmos, okay? Because there's one kind of number that we haven't talked about yet. So we've been able to make the graph narrower, and we've been able to make the graph upside down. How do we make the graph wider? Well, there's one type of number that we haven't seen yet. And I'm hoping some of you may have been able to figure it out. We've seen numbers greater than 1. We've seen numbers that are negative. What's the only kind of number we haven't seen yet? And that kind of number is a fraction or a decimal. So what happens if I do 0.5 times x squared? Sorry, there we go. Look at my blue, or this parabola, compared to the red or this parabola. The blue parabola, this one here, is wider than this one. Now, why is that? Well, I want you to look at this coordinate right here and this coordinate right here. Now, I don't know why they're not showing up. Usually they stick there, but maybe it's because I don't. Okay, so you know what I'm going to do to help us see them? I'm going to do a table. And I'm just going to do 1, 1. And then I'm going to do 1, 0.5. Just so we can see those 2 points, okay? The original parabola's table of values, y is equals x squared, gives us at 1, 1 squared is 1. So the original parabola's height is 1. We're multiplying the y values by 0.5. That's what this equation tells us to do. Multiply the x squared, or the y values, by 0.5. Well, 0.5 times 1 is half of 1, which is this point right here, which is 0.5. Okay? So if we look at 2, 2 is usually 4, which is right here. Now, I can't make that point show up, and I don't want to take the time to do it in the table of values, okay? But half of 4 is 2. So if I'm having all of the heights of the regular points, that squishes the parabola down. And we call that a compression, okay? So we're squishing the parabola down by causing it to be a compression. So let's go back to our smartboard, and we'll summarize that information as well. So if A, now we have to be careful when we write the word decimal. And I'm going to write or fraction. So what do I mean by we have to be careful when we write the word decimal? 1.5 is a decimal, 3.7 is a decimal, but 3.7 is greater than 1. That would actually stretch the parabola. We want to squish the parabola down, okay? So what kind of decimal does that? 0.5, 0.75, those are decimals or fractions that are between 0 and 1. So I'm going to write example 0.5, 0.75, etc. Okay? So if A is a decimal or a fraction between 0 and 1, the parabola, now the word we use for squishing in math is compression. I don't know if anybody's ever worked with a shop. I'm forgetting the word for them now. Press, a shop press. Okay, when a piece of metal is pressed downwards, it flattens out and gets wider. Okay, that's the same idea here. So compression downwards, and just to show what happens, here's a regular parabola. Here's a compressed parabola. Okay. So we're almost at the point now where we can actually solve that problem. But this video is actually already getting fairly long. So what I'm going to do is I'm just going to start us off. We're going to go back to Desmos here. And I'm going to turn the original puzzle graph back on. And I'm going to erase everything else. Okay. So this is the original puzzle graph. I'm actually going to turn that off too. When I turn on my y equals x squared, we can clearly see that it's not in the right place. So how can we get it to move to the right place? So the first thing I want to talk about is we have to slide the vertex, which is at 0, 0, up to this point here, which is at 6. So how do we slide things upwards? Well, if I add plus... Sorry about that. Okay, I'm going to use the keyboard because the keyboard on the screen because I'm having trouble finding the keys on my keyboard. So plus 6. So now I've got the parabola up where it's supposed to be. The vertex is where it's supposed to be. The problem is it's not the right way. It's a smile shape parabola. We need it to flip upside down. Well, how do we get it to flip upside down? Well, the a value, which is in front of the x squared, has to be negative to do that. So I'm going to put a negative. Well, now my parabola is starting to look like my puzzle. So how do we figure out how wide it's supposed to go? Well, now the puzzle originally said without technology. Now with technology, we can get pretty close. I need to make this compressed. It has to go wider, which means compressed. So I know I need to have a number between 0 and 1. Well, let's try 0.5. Well, that's getting closer, but it's not quite close enough, right? So should my number be bigger than 0.5 or smaller than 0.5? Should I try 0.25? Well, let's see what happens. If I put a 2 in front of that 5, wow. So it looks like a smaller decimal makes the parabola wider and gets it pretty close to those points. So I'm going to leave this as a bit of a mental challenge for you here. Now you could do this on Desmos and you could get pretty close. What kind of decimal are we going to need there? But there is actually a mathematical algebraic way that we could figure out exactly what that number a should be. We already know it's negative. We already know it's a decimal. But what should that decimal be exactly? And what I'm going to do is I'm going to make a follow-up video that's going to show how to figure that out algebraically. Okay? But there will be some homework tonight. Just practicing the idea of making things compressed or stretched. And you're going to most likely be having to change the y values in the table of values to be able to figure that out, as I showed during the lesson today. So that'll be it for today. Have a great day, everyone, and we'll talk to you soon.